types of waves that we experience on an everyday basis. The two types are transverse and longitudinal. And they earn their names are related to particular properties of the wave. This is too small. Longitudinal. That looks more visible. Okay. Transverse and longitudinal waves. Transverse waves, examples are a water wave or a light wave. Well, what defines a transverse wave is that there is displacement perpendicular to the direction of motion, meaning that the wave might be traveling this way, but then it's oscillating perpendicular to the direction it's traveling. We can demonstrate this with a slinky. We can demonstrate both types of the slinky, but transverse, it looks like this. If I just go like this, the wave travels down the slinky, but then the pieces of an individual piece of the slinky is moving, this way. There you go. And I can do a continuous, keep applying energy to do a continuous wave, or send a wave pulse. It's called a wave pulse if you just do one. That's what a transverse wave. Longitudinal wave. Oh, and water, is like that because water waves head toward the shore, but the water is moving up, as it goes. Water waves are also longitudinal because underneath the surface, longitudinal waves, the displacement of particles is parallel to the direction of motion. Water and sound are examples of longitudinal waves. Displacement is parallel to direction of motion. And what happens with a longitudinal wave is that so a transverse wave looks like our typical sine wave. Longitudinal wave, it's harder to draw, but if you have like particles, what happens is that they're kind of spread out, and then at certain points they get packed in more densely. They compress, and then at other points they get spread out more again, and then they compress. And these compressions are equivalent to the maxes or mins of the places of greatest whateverness. So you have these compressions, and then the places where they're further spread out are called rarefactions. And what that looks like on a slinky is if you push it straight down. If I push, then where I push, there's the coils of the slinky get pushed closer together, and then, like this coil moves down and it pushes this coil, which pushes that coil. It's sort of a domino effect. Longitudinal waves are that sort of domino effect. And that you can see that the individual coils of the slinky are only moving horizontally, and so that displacement is horizontal, and that is also where the wave is traveling. And again, I can set up a continuous sort of wave, or just send a pulse down. Now, it is much easier to visualize things in terms of a transverse wave. So if we're diagramming or doing calculations or thinking about it, typically we will draw a transverse wave, even if it's a longitudinal wave, because they are analogous. Let me draw a more let me more carefully draw a wave here. So this is the midline. Then we go here, here, no. Right, I just want to draw a couple wavelengths here. All right. There are a few key words, key vocabulary terms. These peaks of the wave are called crests. The maxes are crests. The mins are called troughs. Wavelength is the length of the wave. This is we use the Greek letter lambda, and that is the distance between wave fronts. So if we have our wave, like in a water wave, it would be the distance between one peak and the next. This is a wavelength from crest to crest. We could also measure from trough to trough, or from 0 going up to 0 going up, or from 0 going down to 0 going down. Any of those are wavelengths, and you can kind of see that they're all the same length. Right? Yeah, so that's the distance over which the wave repeats. Period is kind of the same thing it was for rotational motion. It's just the time for one wavelength to pass a given point. So, if I'm creating oscillations this way, it's the time it takes at a single point for us to go from peak to peak, or trough to trough, or whatever. In other words, it's the time for a wavelength. And then frequency is still one over period. It's still the number of wavelengths per second, just as it was for harmonic motion. Wave speed is an important property of the wave. Typically, waves travel pretty much at constant speed. They don't accelerate or decelerate a whole lot, and so our wave speed is just distance over time. And a handy distance that we can use is the wavelength, and the time for one wavelength is the period. So we can say velocity is wavelength over period. And since period is frequency is 1 over period, we can also call this wavelength times f. So whatever is convenient there, we can use. So any calculations we're going to do here are very simple. You get a velocity, plug it in, and get a velocity in period, you can find wavelength. You get a velocity in wavelength, you can find frequency, or whatever. It's pretty, calculationally, it's very simple. Waves can also travel down a string. If you've got a string here, I can make a little vibration. I don't know if I can make a vibration slow enough that you can see it on the camera, but you can send a wave pulse down a string. And on a string, there are two things that are important: mass and tension. And they're important because as tension goes up, speed goes up. As mass goes down, speed goes up. Yep. And it kind of makes sense. Well, the more taut it is, the faster the wave will propagate. Propagate means move forward. That's a term that we'll use a lot with waves. So maybe I should write that down. Propagate won't be asked to define it or anything, but I'll just use it a lot, and the book uses it a lot as well. This means move forward. So tension goes up, velocity goes up. For mass, like, the more mass the string has, the more inertia it has, and so the harder it is for it to go from here to, like, you know, to have that wave pulse traveling down it. It takes more oomph, as it were, to get it to go up, and so that's why mass slows down a thing. But it doesn't really matter, like, what's moving is not the entire string, it's a piece of the string. So really, it's not mass that's important, but it is the mass per length, which we call mu. Mass over length of the string. So the mass per unit length. So that is what comes into play. Because T is already taken for period, tension in this context we'll call F. It's a force, so I guess it works, and we don't use F for capital F for anything else when we're dealing with waves. So these are related to velocity. If we do some dimensional analysis, we can figure out that velocity has the same units as the square root of force over mu, and then experiment indicates that velocity is in fact equal to force over mu. So the velocity of a wave on a string is force over mu. You know, I like to ask you concept questions related to this, related to our equations. Just keep in mind that the square root is here. So for example, if F doubles, then V increases, doesn't double, but it increases by a factor of root 2 because the F is square rooted. If you want to double V, you'd have to quadruple the tension, or cut the mass per unit length by a fourth, or double the tension and cut the mass per unit length in half. You know, so keep in mind that square root is there when we're talking about those ratios. Waves can also be reflected, and they reflect differently depending on what's going on, depending on what is happening at the end of the wave. I've got a string here that I've attached to this. This is our plumb line when we did our marble launch thing. And if I send I don't know if you'll be able to, how it'll work out here. If I, the string is too light. It travels too fast, so you can't really see it. Okay. Well, I'll show you this later. I'll show you this in class. But for reflections, if the end of the string is anchored, like say it's tied on right here, if the end is anchored, then the wave reflects upside down. Meaning, I send a pulse down, then when it bounces back, it will reflect to the other side. If the end is not anchored, like say if I had for example, say I had like a ring stand, and my string was kind of loosely tied around and free to slide up and down, then the wave reflects right side up. So I send a wave pulse down, and it'll reflect back in the same, facing the same direction. It's going this way, this is going this way, and now it's going that way.